All right, so let's now get started into another example, and let's call that example 2. So let's spend some time reading the wording description of our example 2 right here. So in the beginning description of our example 2, we are given mean walking speed is known to be 3.1 miles per hour with standard deviation 1.25 miles per hour. A sample of 50 people was collected as the beginning of our part A right here. Find the probability that the mean walking speed of this sample is above 3.47 and of course miles per hour. And so from the given information, this is what we can draw out right here. So right here in the beginning, if we're looking back at the beginning description here, the wording say mean walking speed is known to be 3.1 miles per hour. So it's indicated here that we have some kind of mean value. And then, but furthermore, this mean value is given without an indication of how big our sample is. So in other words, my point now is that this mean walking speed known to be 3.1 miles per hour here is regarded as a population mean value. So this is everything we know about the beginning description of our beginning population. And now we have, along with the given mean, population mean, we have a population standard deviation of 1.25 miles per hour. So now on my writing board, now I'm going to go ahead and sketch down the information regarding our beginning population, the population where we pick samples from. So in this beginning population, now I'm going to use a random variable x to represent, how about the walking speed. The walking speed of a person. So the value, any value represented by this random variable here is the individual speed of one person. And so in that way of understanding, what we have here is a population of value here. It's a population of walking speed. And so in that way, from the information that I highlighted previously on the computer screen, then we had a known mu being, so mu, a given mean value to be 3.1, and along the way we had a given average spread standard deviation to be 1.25 miles per hour. And so this is everything we have and everything we know about the beginning population. And again, I keep using that term, the beginning population, simply because from this population we are picking our samples from. So now let's begin reading into the description of part A, where it begins our understanding regarding the sample. And so now on the computer screen again, a sample, as in part A right now, a sample of 50 people was collected. Find the probability that the mean walking speed of this sample is above 3.47. And so now we have seen a situation like this, similar to this, back in example 1. So from a beginning population, we're now going to collect a sample or select a sample, and this time the sample here is indicated to be of 50 people. And so immediately we know that we are at sample size capital N equal 50. And then in a sample this way, in a sample of 50 people, now we would like to measure the mean walking speed within this sample of 50 people. But then again, very similar arguments with with the kind of situation in example 1, then here we must realize that our sample of 50 people here is not the only sample. Indeed, it is one among infinitely many other samples, where provided that each sample was already chosen at 50. And each sample itself has a sample mean, and sample mean values can be different or the same. So now generally we can regard to all of those sample mean walking speed in any group of 50 people as a random variable capital X bar. Many textbooks just define a random variable capital X bar, but I myself go a little forward, a little further, to use a subscript here to indicate the sample size in each sample. So now in my notation, capital X bar 50, here is the random variable to represent the mean walking speed. So it's still walk speed, but this is the speed that's already after we average out 50 people. Difference with the speed individually for each person here. So the mean walking speed of a group, or I should have said sample, but it's the same meaning with being a group, of a group of 50 people. It's probably me that I hesitate to use the word sample on people, so I use but it means the same thing. So here capital X bar 50 here represents the mean walking speed of a group, specifically to any group of 50 people. And so with the key steps being highlighted in example 1, throughout example 1 here, and we have already seen how it worked and have seen a lot of explanations, then this is similarly a population of sample mean values. It's a distribution of sample mean values. That's another way of saying it. And formally speaking, this capital X bar 50 is called the sampling distribution of sample mean values, where 50 is the size of each sample. And so now, realizing that we have a population, then again, the center of this population, of this data, is regarded as mu X bar, or the population mean of all sample means. That mean value here, from the experience we've learned throughout example 1, then we can quickly find out the value of mu X bar here to be 3.1. Even though, maybe if I have not made it clear earlier, here I have to make it clear again. This mu X bar is not the same as mu. There are two different objects, there are two different centers. This is the center for the population X. This is the center for the population capital X bar 50. But their calculated value will be equal. And so now along the way, the average spread on this population of sample means here, symbolically sigma X bar, or the standard deviation of all sample means, it's a different way of saying it, is calculated by our known sigma value from the beginning population, 1.25. We're now going to divide by square root of 50, where this 50, as another clarification, it is the sample size given in each sample. So calculation of mine came out to be 0.1768. And again, anyone doing this kind of problem, you are on your own. You are on your own responsibility to watch for different rounding requirements for sigma X bar here. Again, this is the average spread of your sampling distribution of the means, of the sample means, and this is the center of your sampling distribution of the sample means here. So we have already found the answers to the two key steps here. However, now when it comes to the distribution shape, we are now heading into finding out whether our distribution of sample means here would be or not on the normal distribution on a bell curve with the center 3.1 as previously found and the standard deviation 0.1768. So that's what we are about to find out right now. But so now here I need to point out something for anyone to know. So let's put another what to know right here. So if this problem we're doing here was example 1, then the reasoning we used there was because we relied on the beginning population being on a bell curve. That was example 1. So if the beginning, so back in example 1 we relied on the fact that the beginning population, so notice there's no x bar here, it's just the plain capital X. So the beginning population, if the beginning population was a bell curve data, so for example in our case normal distribution at 3.1 and 1.25 for standard deviation, if we had this, then this arrow of mine means then automatically we would be able to lead to a conclusion saying that capital X bar 50 would be on the bell curve as well, with centering at 3.1 but standard deviation 0.1768. But now this was the way how we made our reasoning back in example 1. However, notice now, and this is the part where I'm saying we need to know over here, this piece of information was indeed not known. So I have to cross this out, because now if we look back at all that given information that we already had a sketch right here, this information was not given. And looking back at the problem itself, the wording of the beginning description of our example 2 never gave any information regarding the distribution shape of our beginning population. So in that way, that's just what I did right there. We have to take away this reasoning, the reasoning that we relied to back in example 1. Now we have to take it out. So now know that having a bell curve for our beginning data, our beginning population, is not available or unknown. This piece that we were looking for was missing, or in other words, we did not know whether our beginning population was on a bell curve with the provided center and standard deviation. And so now, without knowing this information, then there's still a way to verify normal distribution on our particular sampling distribution here. The sample size, if we now pay attention to the sample size we're using here, n equals 50, or that's indicated as a subscript here, being 50. That sample size there is well above 30. So for viewers and students who are studying with me in this particular course, if you're questioning me where this 30 come from, my only advice for you is that this is some number to remember. And when you're taking a more advanced course in statistics after this course you're learning with me here, then you will be able to find your answer there about where this number come from. But so now we take that as a rule, that in case our valuable piece of information regarding distribution shape of the beginning population is missing, like this case right here, then gladly here in our case we have a sample size being above 30. That is all the reason that now leads to, I can now say that, so because the sample size is above 30, so now our sampling distribution, where each sample is at size 50, this sampling distribution is still on the bell curve normal distribution with center at 3.1 and standard deviation 0.1768. And so here it is now, I brought up to your attention a completely different route to verify your sampling distribution carries out a normal distribution shape without relying on the distribution shape of our beginning population. And we rely on the reasoning that our sample size here is a value is a number that's above 30. And so now, after having all that explanation, so now we are convinced that our sampling distribution here of the sample means at size 50 is on a bell curve. And the whole point of doing this now, and I put a check mark here, is to indicate that this is now verified. So the whole point now is to draw for ourselves a bell curve where the horizontal lines here represent all values low and high of any sample means out of size 50. And we have a bell curve drawn over it. And as I said earlier, the values that are placed on this line is a sample mean at size 50. That's why I'm using the random variable capital X bar 50 right here. Center of this bell curve is at 3.1. But this bell curve has a average spread, sigma X bar being 0.1768. And now with the same reasoning, with the same explanation as how we have seen back in example 1. The question here is asking, find the probability that the mean walking speed of this sample is above 3.47. Symbolic statement or symbolic expression of that is find the probability where we run into a sample mean at size 50. Take value that takes value above 3.47. And so I explain throughout example 1, and here I can briefly explain again that because we are having infinitely many values for this capital X bar 50, or there can be so many different values that happens for capital X bar 50. So we want to specifically find a chance that when we picked up a random sample of 50 people, then what would be the chance that our sample mean in that sample would be above 3.47. But now, once we understand our problem and why we have a problem as such, then this problem just now being proven to be a simple bell curve problem. So on this bell curve that we have already verified for capital X bar 50, and 3.1 is at the center, 3.47 is somewhere to the right hand side because it's higher than the center. And as the problem is indicating here, we're looking for specifically sample mean being above 3.47. And so if we are looking for a sample mean of size 50 being above 3.47, on this bell curve it is represented by the area shaded to the right hand side of 3.47. And so now we can just start working as usual. 3.47 as the low end of our current interval here. And again, notice that this interval has an indefinite upper end here. So from where this low end, I am going to calculate the z-score of 3.47. So 3.47 minus 3.1 and divided by the current standard deviation of our sampling distribution bell curve. So 0.1768. this is our setup for finding z-score of the lower end on this interval. My calculation now came out to be positive 2.09. And so now, as soon as we have successfully calculated our z-score corresponding to this lower end of the interval, that means if we were on the standard normal distribution bell curve, then this center 3.1 is right at 0 z-score, and this lower end of our interval is right at z-score 2.09. And so this probability problem that we're doing here, or as an area problem on the bell curve here, would have answer equals to the probability that on the standard normal distribution bell curve we're having z-score greater than 2.09, or this area on our current bell curve would be equal to that exact area, on the standard normal distribution bell curve shaded to the right hand side of z-score 2.09. And so now obtaining our final answer here is simply just a matter of running the normal CDF command. Now back on our computer screen right here with the calculator emulation. Now I'm going to access my normal CDF command by second variables, which brought up my distribution functions, the menu for all distribution functions in stats. I'm gonna look for option number 2, normal CDF, or whichever option that say normal CDF. Hit enter to select that. So this time our low end of the interval, remind yourself from the writing board that I had, is 2.09. And that was our finite definite low end. And now I'm going to hit enter to move over to the upper end. And so the upper end in our case again is an indefinite upper end. So I'm going to leave that as 1E99 and positive 1, of course. And again, for all of my students who are studying with me, I only teach you to use the normal CDF command when you are working on the standard normal distribution bell curve. So that means we are going to default these two values at 0 for mu and 1 for sigma. I'm going to hit enter a few times. And now we are ready to execute this command. So final answer now came out from the calculator to be 0.018308 and a lot longer. So from the calculator we found 0.018308 and a lot longer. But as I have said many times, unless being specified otherwise, normally I would go with final answer rounded to 4 decimal places in problems like this. And so 0.0183 is my final answer in 4 decimals. And in case your answer is required to be put in as a percentage, then this answer is equal to or is equivalent to 1.83%. So now what it says as a brief interpretation of the final answer here. So now anytime, provided that we knew some information regarding the beginning population of individual walking speeds, then if we pick any random sample of size 50 at size 50, then the chance of having that sample with an average being above 3.47 is only a 0.0183 chance, or out of 100 times picking samples, only 1.83% of times that we run into a sample satisfying this requirement. All right, and now let's look at another problem in example 2 here. And so quickly looking at the wording description of our example 2 here, again, that beginning description remains exactly the same as how we had it back in part A of this current example. And so just briefly, we can see that the mean walking speed is known to be 3.1 miles per hour with standard deviation 1.25 miles per hour. And so this beginning description right here, in other words, gives a description on the beginning population, the population of individual walking speed where we would collect any of our sample from. And so quickly on the writing board here, I still retain all of that information. And so from what we already knew from part A, then this population representing the walking speed of any individual person, we had a known mu, a known population mean, and that's acting as the center of this data. And we had a known standard deviation, sigma equals 1.25 here, and this is the average spread. And I further addressed and gave hopefully detailed enough explanation earlier in part A that we did not have the distribution, or in other words, we have an unknown distribution shape. We did not know whether or not our distribution of the beginning population was on a bell curve or not. So we did not have that information, and that's the reason why it's in the red box right there. And so now back into the beginning of question B right here. Then from the population of walking speed, so the population of people where anyone is having a walking speed, and now we're gonna pick a sample. So a sample of 100 people was collected. And so now with that information, immediately we're now changing to a larger sample size compared to part A. So in our sample now, it has 100 people in each sample. And so the very same explanation and the very same argument that was made in part A, now I can define a random variable that's called capital X bar. And in my style, I'm using a subscript 100. This is the sample size that I'm using as a subscript right here. Many textbooks in the market doesn't have this, and they only have just the ordinary capital X bar as a variable to represent a sample mean. But no, so in any sample out of size 100, we can find a sample mean. And so that means we will have a lot of values, infinitely many values for sample means at size 100. And so for that, and so in that reason, we regard all of those sample mean values as generally a random variable capital X bar 100. So here as a meaning of capital X bar 100, let's quickly write it down here. This is, it represents the mean walking speed of a group of 100 people. And if anyone is viewing this video lesson here after the lesson that after seeing my workout on example 2 part A, then you can see that this definition of capital 100 X bar is almost identically the same with the definition of capital X bar 50 that we did in part A. The only thing here is that this capital 100 right here represent this subscript 100 right here represents the sample size as being 100 people in each group. And so now, very similar, again, realizing that what we have here is a sampling distribution of all the sample means, or another way of seeing this, of understanding this is a population of sample mean values. Then the center of this data, mu X bar, of course, being different with that center, but final calculated value will equal for sure 3.1, which is the same value with 3.1. But once again, these two are different mean values. This is mean for x. This is mean for capital X bar. And then similarly, the standard deviation or average spread on this population of sample means here, symbolically sigma X bar, can be found, can be calculated by with our known standard deviation from the beginning population. I am going to divide by square root of 100 this time. The math came out for me 0.125. So this is my average spread on this population of sample mean values. We already found the center and we found the average spread. So for the next key steps before being able to find the actual answer, we want to decide whether capital X bar at sample size 100 would be normally distributed or would be placed on a bell curve taking center 3.1 and standard deviation 0.125. So now we are about to find this out. So now again, reminding that we don't have, or we have an unknown distribution shape of our beginning distribution. But gladly, our sample size currently used here is 100, which is well above 30. So in that case, with this reasoning, we now no longer need to rely on the sampling. We no longer need to rely on the distribution shape of our beginning population, but instead we can just make a straight conclusion that this sampling distribution of all the sample means at size 100 will be on a normal distribution, 3.1 center and 0.125 for average spread. And at this point right now, it was still a question mark, but now with this sample size being above 30, it guarantees that we will have this satisfied. So now we checked our third key step like that. And so now the entire usefulness of being able to verify capital X bar 100 can be placed on a bell curve here is that now we can imagine that we are on a bell curve with a nice peak in the center. This bell curve, the horizontal line of this bell curve here represents any value that we can find for a sample mean at size 100. Center is in the middle, being value at 3.1, and average spread on this bell curve, symbolically sigma X bar, is 0.125. All right, and now with a lot of known information regarding our sampling distribution of the means here being on a bell curve with center at 3.1 and with average spreads 0.125. So again, I need to re-emphasize that we must further realize that any sample we picked for at 100 in sample size will have a sample mean, but the sample mean value we picked from a sample is only one sample mean values among infinitely many other sample means here. So the entire purpose of this problem now is that back in the wording, find the probability that the sample means anytime we pick a sample of 100 people, the sample mean of that sample is above 3.47, and of course 3.47 miles per hour for walking speed. And so that means now it makes perfect sense that as a symbolic statement, we're looking for capital P in parentheses X bar 100 being above 3.47. But again, because we're having infinitely many values for this kind of sample mean, and that's the reason why this kind of problem exists. We just want to find out the probability where any sample mean we picked up falls in a desired interval of value. So that interval of value on this bell curve, let's say 3.47 itself is somewhere to the right hand side of the bell curve center here, and then looking for specifically mean walking speed above 3.47, it is graphically represented as an area shaded to the right hand side. Okay, and so now all of a sudden we realize that this problem brings us back into a problem on the just an ordinary problem on the bell curve where we are finding area. So now I am going to find the z-score for my interval values right here. So 3.47 is the low end of this current interval, and notice how this interval does not have a finite upper end right here. Instead, it's having an indefinite upper end. So with the lower end that we're currently having, I'm going to subtract the mean in the middle and divide it by the current average spread on this bell curve, 0.125. And so z-score for this will come out to be, the calculation of mine came out 2.96. It's a positive 2.96. And so that is the z-score corresponding to this value if we were on the standard normal distribution. And so once again, just a quick reminder, but so this center, if it was on the standard normal distribution, then it would be equivalent to z-score 0. And so our lower end of this current interval here, if it was on the standard normal distribution bell curve, then this value would be equivalent to z-score 2.96. And so that means the answer to this probability question, or the answer to how big this area is, would be the same or exactly equal to the answer to the probability question where on the standard normal distribution we're looking for z-score above 2.96. And so now I'm finding that final answer here is only a matter of running our normal CDF command. And so now on my calculator screen right here, on my TI 8384 calculator, I'm going to go second variables, which brings up the menu for all the distribution functions in statistics. I'm going to scroll down to option number 2 that says normal CDF, and I'm going to hit enter. So lower end this time, I am going to provide 2.96, and for the upper end, it's going to be, since we're having an indefinite upper end, the way of giving it 1E99. And now again, as I have mentioned many times, for students in my class, I am going to ask you to default these two values at 0 for mu and 1 for sigma, because we will only use this normal CDF command to work as if we were on the standard normal distribution. And so now with the final answer currently being shown on the calculator screen right here, then that amount of area in the long decimal expression is 0.001538 right out from the calculator. 26 and a lot longer. But now, as I have explained many times before, then unless being specified otherwise, I'll normally round the final answer to any of these area problems on the bell curve to 4 decimal places. So 0.0015 is what we're looking at for the final answer in this case. And in case your final answer is required to be written as a percentage, then this final answer is equal to a 0.15%. Not even a 0.5% here. And so now, as a final interpretation, brief but hopefully understandable enough, that so anytime we're randomly picking up a sample of 100 people and measure their mean walking speed in that group right there, provided that we picked up the samples from a beginning population with all these known properties, mu at 3.1 and standard deviation at 1.25, then the chance of having our sample with the sample mean being above 3.47 is only either understood as a 0.15% chance, meaning you're doing that 100 times, you only get 0.15 times of getting a sample means satisfying this requirement. Or in decimal, it's a 0.0015 probability.